Test, test.
Thing is working.
It's working. Okay, so it's on. This one is working, but
Yeah.
this one is not.
Good morning. My name is Federico, and I'm one of the PCs, and I'm also the chair for this session. Today, we're very happy to have Professor Daniel Cremers with us to give his keynote. So Daniel Cremers received his PhD in computer science in 2002, from the University of Mannheim, and he spent 2 years as a postdoctoral researcher at UCLA. He was then associate professor at the University of Bonn, and since 2009, he holds the chair of computer vision and artificial intelligence at the Technical University of Munich in Germany. He's a recipient of several ERC grants, including one starting grant, a consolidator grant, and an advanced grant. He received several awards, including the Leibniz Award, which is arguably the biggest award in German academia. He's done very seminal work in the field of computer vision, in particular 3D computer vision in areas such as SLAM and 3D shape analysis, and today we'll give a talk on 3D computer vision for dynamic scene understanding. Thanks for being with us today, Daniel, and the stage is yours. Thank you.
Thank you. Thank you, Fede, for the nice introduction. Thanks to the organizers for having me here. It's a pleasure to be here. And I think this audience is just the right one for this kind of talk. It summarizes work that's been done by a number of current and former students of ours and also external collaborators. And so I want to use this opportunity to thank the people who actually did most of the work that I'll be presenting now. And I want to take a bit of a historic perspective on going back about 2 decades. Around 2005, we started collaborating with Mercedes, putting cameras into cars to film what's happening in front of the car. And this is, scenarios that we're all familiar with from everyday life. You drive down the street, and then out of nowhere, something comes rushing into your driving corridor. In this case, this is a PhD student. You're laughing. As Fede mentioned, a lot of the research we do is funded by the ERC. And if you've ever written an ERC proposal, they want high risk and high gain. Now, I don't know about high gain. This is always challenging, but this is, as high risk as you can get, right? Sacrificing your PhD students for research. So we put the cameras in, first 1 and then 2 cameras, and then we started developing all sorts of algorithms back almost 20 years ago to understand the world in front of the car, to reconstruct the 3D structure. This is a scene flow approach that reconstructs things in practically real time at the time, 20 years ago, using GPUs to do the computations. And it also estimates the scene flow, so the 3D motion. This is color-coded here. Red is moving, green is stationary in world coordinates, so we can also subtract the ego motion of the car here. And this motion information, jointly with the 3D structure information, is vital to understand what's happening in front of the car, to make predictions, to anticipate what's going to happen next, because you can extrapolate that motion and say if that same obstacle keeps going with the same velocity, then it will be in the driving corridor in the next seconds. And it's no secret to say that the more a machine can anticipate into the future what's going to happen, the better it can react and help us avoid accidents. And these technologies were then subsequently actually put into products at Mercedes. This is one line of work, autonomous cars, driver assistance. At the time it was called advanced driver assistance. I guess there was a basic driver assistance before, And now it's more towards self-driving cars, ultimately. So this is one area that we've worked in for about 20 years now. Another area that we also started working in almost 20 years ago, in fact in 2007, are drones. This is a picture back from my office in Bonn where I had students assemble drones. You could not buy them commercially at the time, so we had to actually assemble them ourselves. And I can tell you, I never flew one of these because they were very unstable. The low-level control was quite shaky. The only person who could fly it was the guy who developed it, who built it. But then in the subsequent years, drones became commercially available. We started putting cameras on them. We started putting various sensors. And we developed techniques such as this one. This is work by Jacob Engel and Jürgen Storm. where they use the onboard sensors, in particular the camera, the IMU, the ultrasound depth sensing or pressure depth sensing device, in order to build a map and to localize the drone and fly autonomously trajectories like this one. And the mapping here, you see it on the bottom right and left. This we used PTAM, a very amazing technology developed by Klein and Moret in 2007, ISMAR. And but we found in the process of working on it that the precision of these SLAM systems was not sufficient for what we wanted to do. It can localize in a certain environment, but if you really want to go out of the room and come back, it would start to lose track. It would start to drift. But we showed that you can use, we developed our own SLAM methods. I'm going to come to that for this purpose. Here, for example, this is using a technique we coined LSD SLAM, large-scale direct SLAM. It allows in real time to map the whole room around it. And then we went further and computed occupancy maps, volumetric representations of space, distinguishing occupied and free space, developing, maneuvers that allow to maximize the estimated free space, and going further, actually, to trying to compute, do path planning and exploration of unknown environments. And so what you see here is that the algorithm can compute in 3D a shortest path to get to some interesting area, and you see it in the video in a second. That allows it to really fly out of a room through the doorway fully autonomously. And so these were the first steps using, I think, 3D vision to explore the environment, to do autonomous navigation, autonomous exploration, path planning, and the like. This is, we did work on this, on autonomous systems over the years. The field of autonomous driving, if you look at it today, 20 years later, it's really picking up momentum. It's a long, road to autonomous driving. But what we see is there's now quite a number of companies around the globe, companies like Super Cruise and Waymo and others, Aurora, for example, that are putting various, or Tesla, that are putting various autonomous cars of different levels of autonomy on the roads. And in parallel, we see that along with it, there's legislation being put in place across the globe in different countries, in Germany, in the UK, in France, in the US, that actually allows for these systems to be deployed in the middle of human traffic. But one of the challenges that we see still there is that testing and validation remain unsolved problems. You develop a tech stack, you develop a self-driving car, how do you know it works? And there's typically two ways to go about it. One is you just put it on the road and see what happens. And we've seen a lot of companies do that, and sometimes with devastating consequences. People get killed, and that's not only bad for the people who get killed, obviously, but it's also quite damaging to the reputation of respective companies, and the licenses get revoked, etc., and then they're stuck, right? So this is not an easy way to go. The alternative is that you test and train and develop your system in a simulated world. But we all know simulations are not the real world, and there's a big gap, and it's not always clear what that is. And I've seen in computer vision people focus on photorealism. They create simulations like the Carla simulator that allow very photorealistic videos and images. But sorry to say that, it's not the real world, even if it looks real, and we shouldn't get fooled. And I would certainly never sit down in a car that works perfectly in a simulated world. The world we live in, last I checked, is not a simulation. Who knows? And the challenge is really, if you want to deploy self-driving cars in real-world traffic, these self-driving cars need to understand how humans behave, right? How drivers, how cyclists and pedestrians behave in traffic. And the world we live in is just a very complex world, right? And so the question is, how can we capture that complexity and make it accessible to machines so that they can anticipate how humans behave? And I would argue that is the biggest difference between self-driving cars today and human drivers. As a human, I constantly anticipate what everyone around me is doing. And I would argue experienced drivers have that significant advantage. You all know if you get your driver's license, typically within the first year you have most accidents. Why? Because you haven't learned to anticipate how others behave. And this anticipation is something that I feel for myself is very important, that I can predict what the different cars around me will do next. And that requires some model knowledge, and we need to develop and acquire that model knowledge from the real world. And this requires capturing the 3D world and its dynamics. In this talk, I'm going to tackle this challenge in two parts. I'll first talk about capturing the 3D world, the static 3D world, if you will, and then I'll talk about capturing the dynamics of it. Now, capturing the static 3D world, I don't go in all aspects into history, but let's delve a bit into history. This is history that all of you know. This is an Austrian mathematician by the name of Erwin Kruppa, and more than 100 years ago, he proved that if you observe 5 point pairs in two views, corresponding point pairs, you can recover the relative motion of the camera and the 3D structure of these points. And these kinds of works, more than 100 years ago, pioneered, the way and led the way and paved the way for 3D computer vision emerging in the 70s and 80s, and paved the way for techniques that we all know, like bundle adjustment. And I haven't really checked how old bundle adjustment is. It's very old, right? I've always thought this is a solved problem by now. But, often in research, it's my students who tell me, no, things are not solved and you can always do better. And so just to give you an example, this talk is not about bundle adjustment, but for those of you who are interested in this, we did a number of works headed by Nico Demmel here on what he calls square root bundle adjustment, and you can see it. And this is just a glimpse of this paper, one of them. We use so-called null space marginalization techniques to dramatically accelerate the computation for large-scale bundle adjustment problems. And we get, you see it on the bottom right, a 42% speed up over the fastest method. And that is a quite significant speed up, I would argue. And there's a follow-up work by Simon Weber and collaborators called Power Bundle Adjustment, last year's CVPR, where again we showed that you can make things significantly faster, 71% faster, and also 5 times more memory efficient by using so-called power series to solve the inverse of the Schur complement matrix. This is kind of the computational bottleneck for solving large-scale bundle adjustment problems, and he devised a completely new numerical framework with matrix power series approximations to the inverse Schur complement matrix that allows significant speed up and significant memory reduction. But as I said, I don't want to go into detail about this works on bundle adjustment. For the sake of this talk, I want to focus on real-time stuff, things that actually can be deployed in real time in a self-driving car. And if you look at structure from motion, or nowadays sometimes called visual SLAM, there's different definitions. I, again, don't want to delve too much into the different definitions of what you call structure from motion, what you call SLAM, what you call visual odometry, but it's all related. It's all about mapping the world and estimating the motion of the camera. This chicken and egg problem that Kruppa looked at. And these are some of the first real-time capable SLAM systems that emerged, I think, around 2000. I know in Stefano Soato's lab at UCLA, they had a demo running in real time, at least when I joined in 2002. It was a bit dusted up, but it was still working. And then there's a lot of pioneering works by people like David Nister. I mentioned the Klein-Murray, Andy Davison, Richard Newcomb, Davide Scaramuzza, also the team around OrbSlam in Zaragoza. This is quite a powerful technique that we love to use. And these have become extremely popular to estimate the camera motion and map the 3D environment in real time. Most of these works follow very closely in Kruppa's footsteps in the sense that they start with 2 images, then they extract points because Kruppa said he assumes that we have corresponding point pairs. So you have to extract points, and then you have to compute correspondence And you know, if you've ever worked in this field, and I'm sure many of you have, you will know this is a very nasty problem. And there's a lot of heuristics that you have to throw at it, like ransack to resample potential correspondences to make sure that the correspondences are correct. And guess what? You never guaranteed that they're correct. And whenever you have bad correspondences, this will propagate into the reconstructions and deteriorate the performance. And so, about a decade ago, no, a little bit more, 15 years ago, we started deploying what we call direct methods, methods that go straight from the raw sensory data to a reconstruction of camera motion and 3D structure. One of these works along this line was a technique, I mentioned it, LSD SLAM, for a large-scale direct SLAM. I don't want to go too much into detail about how exactly it works, but the key idea is very simple. The key idea is you say, find a motion of the camera and a 3D model of the world such that if you take image 1, project it into the world, and back out to image 2, you should have color consistency. And so even though in the end you estimate points in both approaches, the key difference is that the loss function you minimize in the direct methods is a photometric loss. It's a photometric color consistency that drives all the estimations. And so in that sense, it's much more related to optical flow estimation, where you estimate motion based on brightness consistency. And we'd worked on optical flow before, and it was kind of natural for us to go this way. And you avoid this abstraction step of extracting points, of computing correspondence. It's all done basically in one go. Here's LSD SLAM in action, and to my knowledge, this was at the time, 2014, the first large-scale capable SLAM system that really gave very accurate reconstructions. You can see it, you can walk around the block, and you know, you get almost no distortion. There was a component in there that did what's called post-graph optimization that allows large-scale consistency, and so you can get very large reconstructions, all computed in real time on a simple laptop CPU. And it works indoor and outdoor. It just uses one camera. Obviously, you can then generalize it to 2 cameras. You can add inertial sensory information, whatever sensory measurements you have. In a robotic system, you would fuse that, right? But one question is when we develop these systems, how do we actually evaluate their performance? As I mentioned, this is a challenge. You can go into simulations, but my experience in the SLAM world is there are many methods out there that work super well in a simulated environment. But once you take them to the real world, some of them fail miserably. And this is often not clear why that is. Maybe the world is not Lambertian, or maybe the camera is not a perfect pinhole model camera, right? Obviously, it's not, and real cameras have super complicated optics. Do you really want to model all of that? You know, so you need to devise techniques that are robust to the complexities of the world. And so we wanted to test them in the real world and quantify. So we took a lot of sequences here, about 50 sequences. This is Jacob Engel's work. Again, in different environments with different lenses, some more perspective, some more wide-angle fisheye lenses, etc. All are very diverse, but they all have one thing in common. They all loop back to where they started from. And so we don't know where the camera was halfway through the sequence, but we know where it should be at the very end, and so we can compute the total drift for translation, rotation, and scale. And here we evaluated a technique that we call direct sparse odometry. It's the follow-up to LSD SLAM. There are several differences. Again, I won't go into detail, but the key difference is that we do a really joint optimization of structure and motion. In some sense, going back to some of Krupa's ideas, showing that it's a chicken and egg problem, and rather than alternatingly estimating the two, we have one single Gauss-Newton optimization that estimates the camera motion for a sequence of consecutive frames and a 3D structure in terms of this point cloud. The key challenge was how to get it to real-time performance. So it's, in a way, a photometric bundle adjustment, if you will, but kind of stripped down so that it runs in real time. And you see it's not perfect, right? We deliberately switched off any post-graph optimization, any loop closures to see the drift, right? And here the bicycle on the top left, it's reconstructed twice. So there is a drift and you can quantify it, and you can do that for all the sequences you have. And then you can plot these error plots, and we compare to what we considered the top method in the field, and it is still to date considered one of the best techniques, OrbSlam. And we found that the DSO is significantly more accurate. So for example, if you say what is the drift on the best 300 sequences, OrbSlam has a drift of 6 and we have a drift of 1. So it's a reduction by almost an order of magnitude. Similarly, we get more robustness. So if you say you want a maximum error of 2, how many of the 500 sequences can you track with that error? OrbSlam can track around 100, we can track around 400. So again, a significant boost at the time. There is a lot of improved method that came out in the wake of these works. Here, for example, is an extension of this direct visual SLAM, combining, as I said, with inertial information. It's called DMVIO. Lukas von Stumberg is the author here. And see on the bottom left the images. We go through our corridor. We go up to the 3rd floor of our building. And if you've ever been there, you know there is a slide that takes you 3 floors down. And in the middle of the slide is completely dark. There's practically no visibility, yet this system, equipped with just one camera and an off-the-shelf IMU, it can be tracked at completely unprecedented robustness and precision. We can go back up to the 2nd floor, 2 flights of stairs, go back through the corridor that we came through, back into the room where we started, and there is some drift, but it's very small. And this is like a whole trajectory with, 3 floors of a slide, etc. in between. And this works indoor or outdoor, so you can deploy it for cars. There's lots more videos of DMVIO. If you're interested, just check it online. So we thought there is a value in these techniques. This is useful, the capability to track a camera at completely unprecedented precision and robustness in real time. So we thought, let's create a startup and make these technologies available. So this is one of the first startups I created. We've created several over the years. This is Artisense. We raised about 7 million of VC funding over the years. I had offices in Palo Alto, Munich, and Tokyo, and developed a lot of technologies. I'll come to that. The company was acquired in 2021. Here's often people ask me, by the way, why did you sell the company, right? I see my job as an academic to build companies, but actually then running the company for a long time is a completely different problem, and I feel that's not necessarily what I'm best at. So once the company is there, once the technologies are being developed, the teams are in place, then I think it's a good opportunity to have people take over. What did Artisense, or is Artisense developing? It's still around. It develops sensory systems such as this one that involve stereo cameras, IMUs, RTK GPS information that is fused, very well calibrated, synchronized, time-stamped, etc., because you need accurate sensory information, right? And then spatial AI algorithms to process all this sensory data. And just to give you one glimpse, I don't want to talk too much about this, we deployed these sensory systems on a whole fleet of cars, and within just a few days, we mapped 8,000 kilometers of road in Berlin. And we can not only map, but as you can see here, we can tap into neural networks to extract the semantics of this point cloud. I'll come back to semantics later on. But you see, we can create very large-scale maps, semantic maps of the world with, and I think this was important for the commercial world, with very cheap sensory systems. We don't need huge LiDAR scanners, etc., but just off-the-shelf camera-based systems to create very accurate 3D maps. Now, deep networks came around about 2012, and we've been deploying them for many purposes, for semantic segmentation, for video segmentation around 2018. We did optical flow estimation, FlowNet, many people will know that. So there is a lot of potential for applying deep networks, but it took quite a long time for deep networks to be deployed in this area of visual SLAM. In fact, some of the first methods emerged around 2017, showing that you can train a neural network to estimate camera motion and 3D structure. I'm not sure why it took so long, but something to observe is that a lot of these initial methods were not actually state-of-the-art. So they all showed you can solve the problem with deep networks, but you don't get better than what the classical techniques. And then I would argue, what's the point, right? If you cannot outperform the classical methods, then why would you revert to a learning-based method? So we looked at this problem and we thought there must be a way to integrate deep networks without losing performance and ideally improving performance. And what we developed are hybrid techniques that combine the best of both worlds. So this is one, for example, we call it deep virtual stereo odometry. Actually, in retrospect, that was a really bad decision to call it that because it is not a stereo method. In the literature, many people say, oh, this is a stereo approach. No, this is a monocular approach. It's called virtual stereo because essentially it hallucinates the second camera with a trained deep network. So you train it with stereo, self-supervised. You just need a stereo camera to train it. And once you've trained it, it's a monocular method. It hallucinates the contribution of the second camera. Basically, it predicts the depths from a single image, something that's become really popular over the years, and something that where deep networks are amazingly powerful. You can take a single image and you get a fairly accurate depth prediction. For traffic environments. If this works in the forest, etc., that's a different question, right? How well it generalizes to completely different environments. But for self-driving, it works quite well. Now, this is one thing, but what we did in this method is not only predict the depths with what we call StackNet here, giving significantly more sharp depth predictions than the previous technique by Kuznetsov and collaborators, but then we fed this depth prediction into the SLAM pipeline. In fact, we proposed a variety of predictions here. You can given two consecutive images, IT and IT prime, you can train networks to not only predict the depths for these images, but also predict the relative motion and also predict some notion of uncertainty. I'll come to that in a second. And then you can feed all these predictions into the SLAM pipeline on both on the front end as an initialization, but also in the back end using factor graphs, but also in the back end as additional terms in the loss function. Basically, you're saying find a large-scale reconstruction such that for every keyframe, the depth is consistent with what the deep network predicts. So here's the depth prediction, pose prediction, and once we have predicted depth and pose, we can warp the two images and use intensity consistency as a loss function, which means we don't need any ground truth. It's self-supervised. We just need the video, and again, we say color consistency is what drives everything. Like in these direct methods that I mentioned before, similar loss functions, but now used for training the neural networks. And that allows you to align images to predict depths, but the problem once you do that is for real cameras, brightness is typically not preserved. Something they teach you, brightness consistency, is actually not valid in the real world. First of all, with an off-the-shelf camera, you have aperture changes, and that will lead to significant changes in the brightness, but you can train a network to also predict this aperture change with two parameters, an affine correction for the brightness, A and B, for these two frames, that aligns the two frames in brightness. And then you have more brightness consistency, and that should be fine if you are in a Lambertian world where the brightness doesn't change with the viewpoint. Now, as we know, the world we live in is not really Lambertian. Mostly, actually, it's fairly Lambertian. That's why our SLAM methods work so well, is because the world is fairly Lambertian, surprisingly Lambertian. But nevertheless, there are areas in images, especially in the man-made world, incidentally, where brightness is not preserved. On glass windows, on metallic structures, on the cars, etc. right? So what can you do? You could now go ahead and physically model the reflectance properties of the world. I would say good luck with that in real time. This is a challenge. It's doable, but in real time and robustly, I doubt it. Not today. So what can we do? Well, again, we can revert to the deep network and say, can you just tell me which areas are likely brightness consistent and which ones are not? And it turns out, yes, you can do that, and you can train what's called an aleatoric uncertainty that we found in works of Kendall and Claude and others. And we deploy this to train this uncertainty, and basically you simply then downweight this loss function with the uncertainty. It's a Gaussian assumption, so you have to have this log sigma term to make sure that it doesn't downweight all pixels, right, to balance things. And once you do that, the system can be trained, as you see here, to predict the uncertainty. And indeed, it lights up on the windows, on the metallic structures, but also in the trees where typically you have motion, and then brightness will not be preserved. And then, as I said, all these predictions are fed into this loss function and into the SLAM pipeline, and then we get out a method that uses a single camera only and is very precise and robust. Here we show it driving down the world in one of the Kitty sequences, I believe, and you can see we can create large-scale maps and trajectories where there's practically no drift when you drive around the block. Here, the comparison to the standard DSO method. It's significantly more accurate because of these deep network predictions. And this is all done with just one camera. No IMU, no stereo, no GPS, nothing, just a single camera. And you can evaluate quantitatively, and you find that indeed this deep learning enhanced SLAM approach actually significantly outperformed the baseline methods. And what's most interesting, looking at the bottom here, on the top we compare to classical and to deep learning based methods. On the bottom you see a comparison of this monocular method to mono DSO, but also to visual inertial DSO and also to stereo inertial DSO, a stereo inertial method, not DSO, called Basalt, which was the state of the art at the time. And we find that we are on par with the state of the art stereo inertial method, even though our method only uses one of the cameras and no IMU. So it kind of shows you that you can use the predictions of a deep network to compensate for missing sensory information. Now, obviously, if you have sensory information, you should use it. But if all you have is one camera, you can somehow compensate with deep network predictions. And once you have a deep network, you can go further and you can ask yourself, can I reconstruct the dense world with this network? And this is work of Felix Wimbauer and collaborators. Felix is also here. If you meet him, he can tell you more about this work. And in fact, he'll be presenting a work this afternoon. This is a network that is called MonoRec, Monocular Dense Reconstruction. And it's a little bit involved, but actually it has three components. The first component builds using consecutive images and aligned with tracked odometry. It computes what's called a cost volume. And this is used to predict the depths of the sea. But then, since there are typically moving structures in the world, if you don't use them, the first version is really nice. It reconstructs a dense world, but whenever you have something moving, it gets smeared out over the world. It's pretty. I liked it. But the guys said, no, we don't like this smearing out of moving objects, so they added a component, a mask module, that filters out the moving objects. It's trained to remove, also tapping into the brightness consistency in this cost volume of consecutive intensity frames. It can figure out those areas that are not brightness consistent and filter them out, and then, based on that, predict the dips. And the outcome is what you see here. So this is kind of a virtual copy of the Kitty world computed from just one camera. So you just have to put a camera into the dashboard, drive down the street, and this approach allows you to basically create a virtual copy of the world. world. It's not photorealistic, you know, compared to what we've seen with nerves, etc. There's better photorealism, I would say, but it's quite accurate. And it raises the question whether we really need LiDARs to sense the 3D world. If this can be generated from a single camera, it might not be as precise as a LiDAR point cloud, but it's significantly more dense, it's colored, which is useful, so you can read signs, etc., right? And I would say the precision may be sufficient for self-driving, for avoiding accidents, etc. And you could now go ahead and say, take a copy of this world and train your self-driving cars in that world that is copied from the real world, if you will. This is a follow-up work. Again, Felix Wimbauer, CVPR last year. We called it Behind the Scenes. The idea here is to go a little bit further and say, can we, beyond just predicting a depth, can we predict a full-blown 3D structure, and in this case, from one single image? And I think that's always been a challenge in computer vision. How much 3D can you get from a single image, right? And here, this approach, it is in many ways related to things like nerves. The key idea is that you predict a density. But in contrast to nerve, it's really a density per view. So you don't have multiple cameras. You create a single image, and along each ray, for each pixel, you want to predict a density. The other difference to nerve is it's really a scalar density. It's not a radiance field. We don't predict the color. Why? Because we have the colors in the video. We don't need to estimate or predict them, right? We know the colors, we can compute the color just by projection into images. And so our goal is just to reconstruct the world, and so we predict the scalar density, which turns out is actually a much easier prediction problem compared to predicting a 4D radiance. And as a result, we can get away with a significantly smaller MLP to do the prediction, and if I'm not mistaken, I think this runs at around 10 frames a second, so it's also significantly faster. And it's trained, again, in a self-supervised way. We tap into consecutive images to basically use color consistency to infer a 3D structure and the density. I don't want to go too much into the loss functions that we use. You can look into the paper for that. But here are some results. On top, you see the input images. And again, the bottom depths, this is a thresholded version of this density that allows us to get kind of a volumetric reconstruction, right? Here, comparisons to depth predictions, you see that whereas the depth predictors like MonoDepth2 predict only the beginning of objects, ours can also predict where they end by learning, right? And this is something we do as humans all the time. When you see a car, you not only have an idea how far it is, but you know where it ends because you've seen cars before. And this can be reproduced in a machine, as you can see here. But what's interesting is all these predictions are single image based, and the fact that there is very little flickering shows you that these predictions are surprisingly consistent over time. I would have expected more flickering actually, but things are fairly stable. And you can, much like a nerve, generate novel views. So here's some examples of novel view generations that we computed from this. For self-driving, but also for other environments. So it does somehow also apply to non-self-driving worlds. The next thing, and this is work coming up this afternoon, and I wanted to give a little bit of a teaser for it. This is work of Heiler and Wimbauer and Muhle and collaborators. It's called S4C, Self-Supervised Semantic Scene Completion. It builds up on this behind-the-scenes work, and it does scene completion. And scene completion is a topic where you're given a single color image, you're given some depth information or LiDAR information, and you're supposed to complete the geometry and the semantics, and like you see on the right. And the way they tackled this, in comparison to all other semantic scene completion approaches, they replaced the voxel grid that people used with a semantic field, like a density field, but for the semantics, right? And the benefit of that is that it enables volume rendering. Much like in nerves, you can render novel views, and that way you can actually predict the semantic field from a single image, because you can train this with 2D losses. You don't need a ground truth occupancy. All you need is 2D semantic information, because you can train it with the projection loss, basically. And then you have losses on the appearance and losses on the semantics, and you can train it in a self-supervised way. And so in comparison to baseline methods, this is very much self-supervised. There is no ground truth 3D labeling. And here's comparison. So it doesn't outperform the methods that use ground truth, but it is fairly on par. Here's the ground truth. This is monoscene. This is SSCNet and LMS CNet, and this is ours, S4C. This is coming up this afternoon, so if you are interested in more details, I recommend that you go see their work. Now I come to the second part: how do we capture the dynamics of the world? So far, most of what I've talked about is assuming static worlds. If there are moving objects, we filter them out, but we don't actually try to capture the motion of objects. And this is very important to capture the dynamics of the world. As I mentioned in the beginning of my talk, if you want to deploy a self-driving car in this human world, you know, the key question is, how do the humans around me behave? And a machine has to know that. The cars, the cyclists, the pedestrians, how do they behave? And the question is, where can we get that data from? And there are different perspectives that you can take on traffic. The most common perspective taken by pretty much all self-driving companies is the vehicle perspective. You put cameras in the dashboard, like in a lot of the things I've shown. But that is very limited perspective, because you only see the car in front of you. And if that car brakes, you have no clue why it brakes, right? And we all know that from every day, right? We get angry because the car in front of us brakes, and you think, why is he braking, right? It's because we don't see what they see. We don't have the complete picture. And this is very important for understanding human behavior and traffic, to get that complete picture. And so there is better data that you can tap into, either surveillance cameras or even drone-based cameras, to record traffic and try to capture and model and understand it. And this is a startup that we created recently, about a year or two ago. It's called Deep Scenario. And the way they proceed is in several steps. First, they reconstruct the static environment using classical, computer vision techniques, structure for motion techniques. Then they detect all dynamic objects in the scene in 3D. And then they can use that data and populate simulation environments that basically reproduce that real world in the machine. And the idea is to offer these data, this simulation data that is copied from the real world, for self-driving companies for testing and training their tech stack. It is important to actually capture these objects in 3D. Most aerial detection is using 2D detection, bounding 2D detections, but we found that for this purpose, 3D is important, because often you have a perspective projection, and then in this case, right, in the 2D detection, it looks like the two vehicles ran into each other, but once you see the objects in 3D, you realize they didn't actually crash. So it's very important to get the 3D bounding box for higher precision. And talking about precision, they did evaluations to see how accurate is. This is taken, using cameras on drones 100 meters up in the air, and it turns out with a 4K camera 100 meters up, you get a precision that is in the range of centimeters. They basically said, how big is this object according to the deep network prediction? And then they looked at, what is the model, BMW Roadster or Porsche, whatever, and they know how long and wide these objects are, and they found that the alignment is quite good. So here's some results, just to show you a little bit results. This is, they can track hundreds and hundreds of objects, identify what objects they are, whether it's cars or trucks or cyclists or pedestrians, etc. And they can, monitor pretty crazy driving maneuvers like this car in the middle, right? Don't ever reproduce that. Don't try that at home. And they can, as I said, track bicycles and people. And this is important to understand how humans interact in traffic, something that self-driving cars need to know. They need to be able to anticipate, if I do this, how is the other car, how is the pedestrian going to react? Because it's a lot of negotiations, as you see here. And then there's accidents that can happen, like in this example, right? See, there's an accident happen. We see a lot of accidents in our videos, something that you rarely ever see in the egocentric perspective, unless you're in the accident and you don't want to be in the accident, right? But once you're in the air, you can just monitor for hours, and that's what they do, right? And you can monitor all sorts of reckless behavior that humans do, right? They don't always adhere to the regulations. Now, a self-driving car that assumes everyone follows the rules, that's very naive, right? That's not going to happen. Not here, and certainly not in Mumbai or wherever, right? And we all know human driving is very culturally varying, right? I don't drive in Mumbai. In fact, I don't even drive in southern Italy. We went to Sicily. I didn't drive. My Italian friend drove, right? Why? Because I don't have the training data. I don't have the experience. I don't know how people behave, right? And I need to have that knowledge to be able to properly drive. And it's obviously the same for machines. They need to be able to anticipate how will people typically behave. And that data is vital. And so we go all around the world. This is footage from the US, for example, but also in Europe, and we record data. Here's another accident. Car on the right, and at last second he decides, oh, I want to go to the left, right, and crash, right? Something I've done many times. You're on the highway, on your very left lane, 3 lanes of highway, and then my wife says, oh, we got to exit here, right? And then I turned over 3 lanes. Fortunately, I never got hit, right? But who knows, one day it might happen. Here, what we can do is we can train self-driving systems to do better. In the exact same situation, we can test a training behavior, an active planner, to see how do we need to configure it so that in the exact same critical scenario, it will not have an accident. And this is what this data serves. We can extract the data, we can populate simulations with it, and we can then use it to improve the tech stack to make sure that it doesn't happen in a simulation where every single agent is a real human being. Yeah. So this is, there's a lot of companies that we work with. And if you're interested in this startup, just reach out to Deep Scenario. So I'll come to the end of my presentation. I talked about our beginnings in the field of driver assistance about 20 years ago, estimating 3D structure and motion. I talked about SLAM, real-time SLAM, direct SLAM methods, and deep learning enhanced SLAM methods. I talked about semantic large-scale mapping using just off-the-shelf camera-based systems. I talked about dense mapping from a monocular camera, how you can get kind of digital twins of the world from a single camera. I talked about this recent work, S4C, for semantic scene completion. Please do go by and ask them about all the details of this work. And I talked in the end about capturing the dynamics of the 3D world in order to understand how humans behave in traffic and how to make that knowledge available for making self-driving cars safer. Thank you.
Thanks a lot, Daniel, for the great talk. We have now time for a few questions from the audience, if there's any. If you have any questions, we also have some microphones. I actually stole yours, so let me give it back to you.
So, very amazing talk. So, you did not mention loop closure, right? So, which will be a very efficient way to address drifting. And I think deep neural networks could be very important for identifying loop closure, right? Because you have this wide baseline scenario, right? Which deep neural networks could be very good.
Yeah.
Can you comment on that?
Yes, so I didn't mention for time reasons, but for example, LSD SLAM has loop closure in it and pose graph optimization to assure global consistency. And I think we may have been the first to use loop closure and pose graph optimization in visual SLAM. We used it, I think, in 2011 for RGBD SLAM. We introduced this concept. It's been used in LiDAR-based SLAM before, but I think we carried it over into the field of visual SLAM. It's very useful, but the key challenge is you need to be able to quickly and reliably detect loops. And how to do that in a scalable fashion is a challenge, but that's where typically descriptors do play a role, because you want something that doesn't increase in compute time the longer the sequence. You cannot compare this image to all previous ones, so you need to somehow do an efficient indexing and tap into to identify candidate images that might be related. But that can be done, and it's been done, and indeed you can use deep networks for computing these descriptors, and obviously that would be the preferred choice. Yeah.
That's another question. Does it? Can you hear me?
Yes.
Yeah, thank you so much for the great talk. So my question is more towards monocular dense mapping. So nowadays it's an era of large video models, and we are basically processing all sort of videos nowadays. So I just wonder, basically, monocular SLAM, if we need to run on completely in the wild videos where we have lots of dynamic objects, how far are we there, and what are the challenges that still need to be addressed? So would like to hear your thoughts about that.
That's a very good question. That's the question I've been asking all my students over the last couple of months. What is the bottleneck that gets our SLAM techniques to work on a random YouTube video? And this is a very important question, right? Why? Because we live in an age of generative AI, and we've seen amazing results from diffusion to synthesize images of super amazing photorealism. And there are now results that enable us to generate 3D structures, dream fusion or other techniques that you can use to generate 3D structures. But if you look at these, they are all trained on 2D. And I think on the long run, we want to enable the capacity to train on 3D. But that requires us to actually generate at massive scale 3D worlds, right? And on the other hand, YouTube is overflowing with videos of that 3D world, right? So if we could just deploy our SLAM techniques on a random YouTube video and get out the 3D worlds that are observed there, that would be amazing. And you're right, they're moving objects, but you notice we have the tools to filter out the moving objects. And we have loss functions that tell us whether things are consistent or not. There's brightness. If it's not brightness consistent, you can say, okay, then maybe the reconstruction failed, and then you can say, it doesn't matter, there's more videos on YouTube. So I think we're now at a time where visual SLAM is at the same verge of where structure for motion was in the age of what they called phototourism. Steve Seitz and collaborators who said, let's not just reconstruct from our own cameras, but let's reconstruct from all the images that are on the internet. And as you know, that created quite a splash. And I expect the same is going to happen if you are able to extend these visual SLAM techniques to work on the internet, black box. And I think that's going to create quite a revolution for a generative AI of 3D worlds. But what are the bottlenecks? Good question. I think all the components are somehow there. Sure, you don't have the calibration of the camera, but it's a few parameters, right? And these networks estimate gazillions of parameters, 3 more, who cares, right? That shouldn't be the problem. So I'm not quite sure what the real bottleneck is. I've been discussing it with a number of my current and former students. I do believe it's within reach.
Hi, Daniel. Thanks for the great talk. So a lot of the things that you're talking about SLAM is you're trying to match human performance in terms of localization, perhaps down to metric, right? Mm-hmm. But have you been thinking about going superhuman, like things that humans cannot do, right? Like we cannot communicate geometric information in between each other, but machine can. So
Yeah, so there's different levels of superhuman performance. I didn't mention that, but most of what I showed is definitely superhuman. For example, our SLAM systems, we can drive around several blocks and the system, even without loop closing, knows precisely where it is relative to the starting point. If I sat you down in the same car and drove 3 kilometers and say, tell me how far we are from the starting point, forget it. Humans never have that. So with respect to visual odometry, we are far beyond what any human can do, far beyond. Right? Obviously, once you then deploy it in self-driving, you can do inter-car communications. People do that a lot. It's an interesting research area, connected mobility, where cars communicate. And that makes life easier, right? If I don't have to guess about what the other car is going to do because it signals its intention to me, then it's much better. Then I can do a centralized, optimization of trajectories using network flow approaches rather than a single shortest path algorithm. I can optimize all trajectories jointly and assure avoidance of accidents. It's brilliant, that world, but it requires inter-car communication. So there's obviously security concerns, right? What if the information you get is not valid, right, or faked or tweaked with, right, by some third party? So there's many challenges there on this inter-car communication, but it offers a lot of potential. And so I think it's definitely the way to go. I'm not super interested in it myself, because my area is more 3D computer vision. But definitely this should be tackled and solved, and it will improve things. So self-driving will be much better once we have no more humans, right? But when is that going to happen, right? In the inner cities, we'll always have bicycles. I don't see self-driving bicycles on the horizon, really. And we'll always have pedestrians, right? So there's the cars, sure, we can make them all self-driving, but, the complexity of the world with pedestrians and cyclists, it's still there. On the highways, yeah, solved problem, I would say. But inner city traffic, for years, we'll have interactions between self-driving cars and humans. And so we need all this knowledge.
We might have time for one more question.
Yeah, I can maybe ask a follow-up question. So now that we are talking about processing these videos, so we know that for many of the videos, lab methods may fail despite filtering out the moving objects. So can you comment a little bit about that how do we understand when a SLAM method has failed?
It's a good question. So it depends on how you tackle it. If you train a deep network, I think it's more tricky. But the classical approaches and also the deep network enhanced approaches that I've presented, they all are based, and this is the core of these methods, on a loss function. And so once you optimize that, you can see what is the loss. And once the loss is too high, something is fishy, right? And then what is fishy? Whether the scene was not sufficiently Lambertian but too much specularities, or whether there were too many moving objects, or whatever it was, or whether you had too much motion blur in the camera, or there was rain on the camera. It could be gazillions of reasons why it failed. The key thing is it doesn't matter. You just move on to the next YouTube video and try that one, right? And once, so I think there are ways to automatically, we talked about it with Andrea, I think there are ways to automatically determine whether something failed or not. This seems to be one big bottleneck at this point, but I think it's doable.
Thank you so much.
Great. I think we have to close the session now. So first of all, let's thank the speaker again. Thanks, Daniel, for the great talk.
Thank you.
We now have a 1.5 hour lunch break, and we'll see each other again in this room.